This is just a quick reminder that you should feel free to pause the video if you ever feel you want more time to think and write. Welcome to section 5.61. This is applications and models, growth and decay. We're going to take this over the course of 2 days. This is day 1. So here's a new equation that we're going to be using a lot. It's how you measure population growth. And there's really 3 variables. The population as a function depends on 3 variables. It's your starting population or your initial population, and then this is the number e. That's 2.7, 1828, 1828, 74, or whatever it is. And then you've got k, which is the exponential growth rate. That's going to be how fast. It's going to be a number that determines how fast or how slowly it grows. T is going to be time, usually measured in years, but that this exponential growth rate is, if this is measured in years, then time is also measured in years. And it is. It will be for all the examples. Here's example 1, population growth of Mexico. In 2011, the population of Mexico was about 113.7 million. And so we can write that down as our knowns and unknowns. Population was 113.7 million, and the exponential growth rate was 1.1% per year. Let's write that as a decimal right here, and then 113.7 goes out in front. That's like an initial population. T is going to represent the years since 2011. So if the initial population was 2011, that's going to be year 0. If t equals 1, that would represent the year after 2011, 2012. So an equation that takes those 2 numbers and puts them in would be right here. And this is the number e, and this will be your variable time. If you want to graph that, this is what it would look like. Graph the exponential growth function. It's here. You can see 113 is at year 0, and that makes a lot of sense given what's going on. Estimate the population in 2015. That would be 4 years after 2011. So when t equals 4, you can plug it into the equation. You get 113.7 times e to the 0.0111 times 4. And this is the output right here. And I've even included on the graph. Oh yeah, here's where you do c. D is going to ask you, after how long will the population be double what it is in 2011? Well, there's 2 ways to do it. You can look at it on a graph, and here's 113.7, and double of that would be 227.4. And you can kind of estimate it on a graph, on a Desmos graph. You can get it exactly as 63. But we could also do it using the equation. Doubled, our initial would be this. 227.4, that's double of this. Divide both sides by 113.7, you get 2. So in point of fact, it doesn't, like the actual, you don't really need to know what number this is. You could just say that this is going to be 2 is equal to this. When is all this going to be a doubling factor, a doubling growth factor? Anyway, you can take the log of both sides, and you get the log of 2 is equal to, well, here, this would cancel out. Taking the log of both sides, or you can also think of this as rewriting this as logarithmic notation instead of exponential notation. Here's the exponent. What is the exponent? It's 0.11t, and that is equal to the natural log of 2, because 2 is the power. Dividing both sides by 0.11t, just by 0.011, you get t all by itself. So t is equal to natural log of 2 divided by 0.011. And so then, therefore, t is equal to 63. That's not the answer. You have to figure out what year. So you add 63 to 2011, and you get 2074. Interest compounded continuously. Here, we're going to talk about interest that's compounded continuously. And what that means is you're going to have interest continuously. You're always going to be gaining money. As it's annual, simple interest means you get all of your interest at the end of the year, at the end of the first year after you've deposited. But compounded interest means you're continually always getting a little bit more money. You're always getting interest. So you don't have to wait till the very end to receive your interest. E is going to be the number that we use, and the interest rate is K, and the P0 will be the initial amount. So if you read the word problem, it looks like this. Interest compounded continuously. Suppose that $2,000 is invested at an interest rate K, compounded continuously. We need to use our formula over here for continuously compounded interest. And grows to this amount in 5 years. So what we know is T is 5 years, P of 5. If you plug 5 into the formula, we should get as an output 25.04 and 65 cents. And the P0 is 2,000. What we don't know is what K is. What is the interest rate, K? So we plug everything in except for K, and then dividing both sides by 2,000, we get this. Rewriting this as a natural log. This 5K is the exponent, so it's over here, and the natural log of all this. This is base E, and this is the power. So natural log of 1.252325, you can calculate that. And in fact, you can divide both sides by 5. So I want you to tell me, what is the interest rate? Calculate this, divide it by 5, and then rewrite it as a percent. And that's what the interest rate is. I'm just going to move on. Growth rate and doubling time. Here's a relationship. You might have seen from the example, one of the lines said T is equal to natural log of 2 divided by 0.011. 0.011 was the K value. Well, it turns out that this can be generalized to any interest rate, growth rate. If you're growing by this amount, if your K value is this, then the natural log of 2 is going to tell you the doubling time. And the relationship is like this. Here it is KT equals natural log of 2. We could have either one of these in the front divided by the other one. Anyway, there's the formula for growth rate and doubling time. The population of Kenya is now doubling every 28.2 years. So that's why you can say that K, the exponential growth rate, is equal to natural log of 2. Remember, it's doubling every 28.2 years. You type that into a calculator and you get this. And that is 0.0246, which is just about as heavy as mercury is. Do you know how dense mercury is as an element? It's crazy dense. It's so heavy. It's like liquid metal. It is a liquid metal. So that's why it's 2.46, because you have to move the decimal point twice. That was your audio check, by the way. Mercury. Begin 5F1, copy the problem list, do the first problem, and I will see you in class.